Today, we're going to learn how to solve basic inequalities. First, let's look at the difference between equations and inequalities. For starters, there's a single equal sign. But when we work with inequalities, you'll see that there are 4 inequality symbols: less than, greater than, less than or equal to, greater than or equal to. An equation is a math puzzle with an equal sign. For example, 2x plus 1 equals 7. The equal sign lets you know that this is an equation. An inequality is a math puzzle with one of these 4 inequality symbols, like 3x minus 1 is less than or equal to 12. We have an inequality symbol, so we call this an inequality. One of the big differences between these two types of puzzles is that an equation will have a finite number of solutions, whereas in general, an inequality will have an infinite number of solutions. So let's see how to solve inequalities. For our first example, let's look how to solve x plus 3 is less than 5. We have a less than symbol, so this is an inequality. And to kind of get us started, I'm going to make a table over here where we'll try different values for x, and we'll check to see, is this a solution? For example, let's start with 0. Is 0 a solution to this inequality? You can find out by plugging it in and see if you get a true statement. 0 plus 3 is less than 5. Is this true or false? It's true. So 0 is a solution. Next, let's try 1. If we plug this into the inequality, we get 1 plus 3 is less than 5. Is this true? It is. So 1 is also a solution. And what about 2? If we plug this in, we get 2 plus 3 is less than 5. Well, if we simplify, this says 5 is less than 5. Is this true? No. 5 is less than or equal to 5, but 5 is not smaller than itself. So 2 is not a solution. And if we did one more like 3, we plug that in, we get 3 plus 3 is less than 5. I'll put a little question mark over that to remind you that we're testing to see if this is true or false. We're not saying it's true or false. Well, this is false because 6 is not less than 5. So 3 is not a solution. So we could keep going. We could start testing out negative numbers. For example, what about negative 1? If we plug this in, we get negative 1 plus 3 is less than 5. Once again, I'll add the question mark. And is this true? Well, negative 1 plus 3 is 2. 2 is less than 5. That is true. So negative 1 is a solution. And in fact, we could keep doing this over and over and over again. We could do this all day, all night, and for the rest of time. And we would never run out of correct solutions. And so this idea of guessing and just trying numbers is not what you want to do. Instead, what we're going to do is solve this much like an equation. First, let's try and get x on a side by itself. To do that, we can subtract 3 from both sides of the inequality. This is using probably the most important principle in algebra. If you have an equation or an inequality, if you do something to one side, you have to do the exact same thing to the other side, otherwise you've changed the problem. Here we're subtracting 3 from the left side, and so we have to subtract 3 from the right side of this inequality. If we simplify, we get x plus 3 minus 3 is just x. 3 and negative 3 cancel, so we have x is less than 2. This describes all the solutions to the inequality. Any number less than 2 is a solution to the problem. And one way we can visualize the solutions is by graphing the solution on the real number line. So the answer to this inequality is all numbers less than 2. So what we want to do to visualize the solution to this inequality is highlight the entire region of the real number line that's less than 2. Well, here is 2, and what I'm going to do is draw a circle. And then what I will do is shade all the region to the left of it and draw a little arrowhead to let everyone know that this continues on forever. 2 things I did here that's important to note. One is I used an open circle. That's the symbol that we use to say this is where the region stops, but we're not including that specific point. And on the left we have the arrowhead to let everyone know that that continues to the left forever. Let's see another example. Let's solve the inequality x minus 2 is greater than or equal to 1. We'll do this more quickly. We're not going to make the table and just try various things. We're going to proceed like we did previously, and that is we're going to solve this much like you would solve an equation. So what we're going to do is add 2 to both sides of this inequality. So we will add 2 here, add 2 here, and when you simplify, on the left-hand side, you're left with just x, and on the right-hand side, we get 3. So the solution to the inequality is every number x, or any number x, that's greater than or equal to 3. And once again, let's draw a picture of the solutions. Now here, what we want to do is to highlight the region of the real number line that covers all those numbers that's greater than or equal to 3. Now here, we want to use a solid circle because that's what you use to indicate that the region that you're drawing, that point is included. So open circle means that point is not included. A solid circle means that point is included. And now we just highlight the region to the right of this point and we draw an arrowhead like we did before. So this is a way to visualize all numbers on the real number line that are greater than or equal to 3. Next, let's solve 4x is less than or equal to negative 12. The previous example we had addition and subtraction. Now we're dealing with multiplication. So to get x by itself, in this case, we divide both sides by 4. Once again, if whatever you do to one side of the inequality, you have to do the exact same thing to the other side, otherwise you've changed the problem. The 4's cancel and we're left with x is less than or equal to negative 3. And once again, if you wanted to, you could graph the solution or draw it on the real number line. In this case, what you'll often do now is just really label the important parts for describing your solution. Here we have less than or equal to. So we use a solid circle because we want to include the number negative 3 and then highlight the region to the left of it. And don't forget your arrowheads. Let's see one other problem. We've covered addition, subtraction, and multiplication. Let's now see a problem that involves division. Let's solve the inequality x divided by 3 is greater than negative 2. Once again, to get x by itself, to isolate it on a side by itself, we're going to have to get rid of the 3 in the denominator. So we're going to multiply both sides by 3. So we'll multiply the left side by 3, and we will multiply the right side of this inequality by 3. 3's cancel, leaving us with x is greater than negative 6. And if we wanted to draw the graph of the solution, that's where negative 6 is. And we want to highlight all the numbers greater than negative 6, but not including negative 6 itself. That means we have to use an open circle, shade that part of the real number line to the right, and draw an arrowhead so everyone knows it continues onward. So here we saw how to solve some inequalities that involve addition, subtraction, multiplication, and division. But there is one little thing you need to be aware of, and that is when you're multiplying or dividing by a negative number. There is one thing that's different than equations. Here is where things do diverge a little bit. So to introduce you to this trick, let's return to the real number line. Now we know that negative 5 is less than negative 2, because as you go left on the real number line, the numbers are getting smaller, and as you go right, the numbers are getting larger. So negative 5 is to the left of negative 2. That means negative 5 is smaller than negative 2. It's less than negative 2. Now what if we multiply these two numbers by negative 1? Watch what happens. If you multiply negative 2 by negative 1, you get positive 2. And if you multiply negative 5 by negative 1, you get positive 5. And now look at 2 and 5. Here, 2 is to the left of 5, so 2 is less than 5. You could also write this as 5 is greater than 2. They say the same thing. So the key thing to keep in mind here is that when you multiply numbers by negative 1, it's like you're flipping it about a mirror at 0. So when we multiplied negative 5 and negative 2 by negative 1, they flipped over to the positive side of the real number line. And on the left-hand side, negative 5 was smaller than negative 2. But on the right-hand side, 5 is now larger than 2. This may not seem very exciting or mysterious, but you want to keep this in mind for the problems that we're about to solve. Let's solve negative 5x is less than or equal to 20. We want to get x by itself, but we're going to do this in 2 steps so we can really focus on what happens when you change signs, where you multiply by negatives. We could just divide by -5. We could do that, and that would be the fast way, but I want to really take it slow here so that we can use what we just saw with things flipping around the real number line. Now, if -5x is less than or equal to 20, that means on the real number line, -5x lies to the left of 20. Now, if we multiply both sides by -1, let's say we multiply -5x by -1, and we multiply 20 by -1. What we saw with the example of -5 and -2 is when you multiply numbers by -1, you're flipping it about the origin, about the number 0. And so while -5x lies to the left of 20, when we flip it, it now lies to the right. So that means by multiplying by -1, the number on the left, -1 times -5x, that does represent a number, is now going to be to the right of 20 times -1. That means 5x lies to the right of -20, or 5x is greater than or equal to -20. So by multiplying through by -1, what we had to do was flip the inequality symbol. That's the main thing to take away here. When you multiply both sides of an inequality by -1, you have to flip the inequality symbol. Now we can solve this much like we did with the earlier problems. We could divide both sides by 5. That gives us 5x divided by 5 is greater than or equal to -20 divided by 5. Now we simplify and we're left with x is greater than or equal to -4. Let's see another example. This one is x divided by -3 is greater than 2. So what we're going to do, like before, is we're going to break it up into two steps. First, we're going to multiply both sides by -1. And again, I'm not going to write the symbol right now. Because we multiply both sides by -1, these numbers now are replaced with their mirror image. That's another way you could think about it. It's either flipping over 0 or it's like the mirror image about 0. And because in the inequality, x divided by -3 is larger than 2, that means x divided by -3 lies to the right of 2. But when we flip them or take the mirror image, their order is now reversed. So that means the left-hand side now lies to the left of the right-hand side. Or the left-hand side is smaller than the right-hand side. The negative signs cancel, so we're left with x divided by 3 is less than -2. We can come up here and multiply both sides by 3. And when you multiply by a positive number, you don't have to worry about things flipping or mirroring. And so the 3's cancel, and we're left with x is less than -6. So I'd like to recap the 6 examples that we just saw. The first was x plus 3 is less than 5. The next was x minus 2 is greater than or equal to 1. Then we saw 4x is less than or equal to -12. Then x divided by 3 is greater than -2. -5x is less than or equal to 20. And x over -3 is greater than 2. I picked these examples for a very specific reason. These first 4 allowed us to explore a basic inequality with addition, subtraction, multiplication, and division. And these 4 examples worked just like equations, except we were replacing the equal sign with an inequality sign. And also I wanted to make sure that we did one problem using each of the inequality symbols. The last 2 were chosen because it involved multiplying by a negative number and dividing by a negative number. And doing that allowed us to talk about how inequalities or solving inequalities is different than solving equations. With equations, if you multiply both sides of an equation by a negative number, everything's fine. If you divide both sides of an equation by a negative number, it's still correct. But with an inequality, if you multiply or divide by a negative number, you now have to flip the inequality symbol.